friends. It's been so many days that we have met. So I'll quickly review, what we have seen in our previous classes. So we're actually looking at the Unit 2. In Unit 2, we have completed the first 6 topics. Okay, all these 6 topics we have completed, and we are actually dealing with this 7th one here. This 7th one, we have started the transient heat conduction. And this transient heat conduction, we have seen some topics, and I'll quickly review what we have seen already. So we have started the transient heat conduction. Transient, the word transient itself means that it is unsteady. Okay, what is unsteady? The given property, in our case it is temperature, and this temperature is varying with time. Okay, so far previous cases that we have considered, all the previous cases that we have considered in Unit 1 and Unit 2 are all steady cases. That is, the temperature is not varying with time. But from now on, in this transient heat conduction, what we do is we actually consider a unsteady state wherein your temperature is going to vary with respect to the time. Okay, and in this transient heat conduction, you will have 3 cases. Okay, whatever the problem that you get in your examination, okay, it will be from these 3 cases. You will be facing these 3 questions. So first, what you have to do is you have to check the given problem, is it belonging to this particular case or not. If it is belonging to this particular case, no, you can solve the particular problem using the methodology followed in that particular way. Okay, so these are 3 approaches by which you can solve a transient heat conduction problem, basically. So here, in lumped parameter system, what is the case? Let us see. See, in lumped parameter system, what you do is temperature will vary with respect to time alone. Okay, temperature is not going to vary with the position. Okay, when I say that the temperature is varying with position, if the temperature is varying with respect to the x, y, z coordinates, then I will say that the temperature is varying with position. But if it is varying with time alone, then I say that temperature is varying with respect to time only. Okay, then if you have to consider both position and time, the temperature will be dependent on position and time. But in our lumped parameter system, temperature is varying with respect to time only. So this is the case with your lumped parameter system. Okay, temperature is varying with respect to time only. It is not varying with respect to position. Temperature is not varying with respect to the position. That is, if I consider a body like this, as you can see here, the blue color line that I have drawn here, that is actually body. So wherever you take, okay, whatever may be the position, it can be X, it can be Y, it can be Z. Okay, whatever may be the position, with respect to the position, the temperature is not varying. Okay, everywhere for a given position, the temperature is same. It is 20 degrees centigrade everywhere. So it is not varying with respect to the position, and if any time, the temperature is 20 degrees centigrade throughout. So this you can call it as a lump. Okay, so there are 3 basic things that you should remember as far as lumped parameter system is concerned. Okay, in the lumped parameter system, these 3 things should be satisfied, and these 3 things should be kept in mind. As I have already mentioned in this particular example, uniform temperature should be maintained throughout the body. Uniform temperature should be maintained throughout the body. Okay, wherever you take, the temperature should be the same in a given body. Then the second thing is temperature gradient is zero. That is the temperature variation with respect to the position is zero. Okay. And these two things will be satisfied only if the material is having high thermal conductivity. If the material is not going to have high thermal conductivity, this particular uniform temperature and the temperature gradient zero is not possible. Okay, the temperature, sorry, the thermal conductivity is very less. Okay, obviously temperature is going to vary if you are giving some heat on this side. If the thermal conductivity is very less for this particular body, what happens, it will not travel to the other side. That is, the temperature on this side will be more and the temperature on the other side will be less. But if the thermal conductivity is very high for this particular body, then what happens? Whatever the temperature that will prevail here will also prevail on the other side. The same is the case with cooling also. So, in order to have a lump, the material should be having high thermal conductivity. High thermal conductivity. If there is less thermal conductivity, then you may not call it as lump. Okay. So at any given instant of time, the temperature is same throughout the body. At any given instant of time, temperature is same throughout the body. Okay, but with time it may vary. Okay, with time maybe at t is equal to 0 second, it is 20 degrees centigrade. Maybe t is equal to 5 seconds, it can be like 22 degrees centigrade. With time, it can vary, but with position, it is not varying. That we call it as lumped parameter system. Okay, in this example, you can see the water is there at 20 degrees centigrade, and in this water, you have dropped a copper cube which is having 100 degrees centigrade of temperature. Okay, so if that is the case, what happens is at any given instant of time, the temperature is same throughout the body. So that can happen. So if you want to actually, uh, find out whether this particular case is falling under the lumped parameter or not, is it really a lump case or not? It can be actually understood using this concept of Biot number. Okay, once you find out the Bayes number value, you can actually tell whether this particular problem will fall under this lumped parameter or not. For that, what we will do is first we will define what is Bayes number and then move on to the next thing. See, Bayes number will be a ratio of convection heat transfer to the conduction heat transfer. Okay, otherwise, what we can write is in the top, if you want to write conduction, and in the bottom, you want to write convection, we can write in terms of resistance also, because heat transfer is inversely proportional to resistance. This way also you can write. So the ratio of convection heat transfer to the conduction heat transfer, if you take, you will get this particular formula. Okay, Bayes number is equal to HL by HLC by K. You will get, how you get this? Heat transfer by convection, if you take in the numerator, it is HA delta T as per your Newton's law of cooling. And heat transfer by conduction is equal to Ka dt by dx. This you will get according to your Fourier's law of heat conduction. So if you take the delta T's out and areas out, what you have here is HL by K. This you call it as a Biot number. Okay, the same thing you got here. This we are calling it as HLC by K, H being the heat transfer coefficient measured in watt per meter square Kelvin, and K is the thermal conductivity is measured in watt per meter Kelvin, you know it. And then LC is the characteristic dimension measured in meters. Okay, so if you take the units on the top, for H it is watt per meter square Kelvin, and for L it is meter, and then for K it is watt per meter Kelvin. So if you take it, what happens is the unit on the numerator is equal to the unit on the denominator. So there is no unit for Biot number. Okay, Biot number is actually a dimensionless number. Biot number is a dimensionless number. Okay. Then, if you want to find out whether the given case is lump or not, if you want to find it out, what you have to do is you have to calculate the Biot number first. Once you find out the Biot number, you have to check whether this Biot number is falling under zero point 0.1 or not. That is, it should be less than zero point 0.1. If it is less than zero point 0.1, you will call it as lump. If it is greater than zero point 0.1, you will if it is the Biot number formula is HL by K. Okay. See, K, we told that it should be very high. Okay. When K value is very high, obviously the Biot number value should fall below 1 in general sense. But most of the experiments have proved that a lumped parameter system will be valid when the Biot number value is less than zero point 0.1. The lump parameter system is a proper way of representing the actual system. Okay, so that's why it should be taken less than zero point 0.1. And then what we are going to do now is trying to derive an equation for finding out the temperature, for finding out the heat transfer, and so on. We are trying to do some derivation here. For the derivation, what you have done is you have taken a lump here. It is there in a so and so atmosphere. It can be water, some liquid, gas. It can be anything. Okay, so it is completely exposed to this particular environment. And then what you have done is you have taken the conservation, okay, the energy conservation, the heat conservation you have taken. Heat transfer out of the body is equal to heat transfer to the ambient. That is, whatever that is leaving the system and and entering atmosphere, okay, leaving system and entering surroundings. Okay. So whatever that is leaving the system, you would measure it using MCP delta T. Okay, MCP delta T is the heat transfer formula measured using the specific heat. Okay, this you will use the specific heat to quantify the heat transfer. Whereas on the other side, heat is entering into the surrounding. Whenever heat is entering into the surrounding, it is a fluid flow heat transfer. When there is a fluid flow heat transfer, you will always quantify that heat transfer using the convection heat transfer column. So HA delta T, you will obviously use. That's what you have used here. HA delta T, that is Newton's law of cooling, you have used here. So, but there is a imbalance of the units on both sides. On your LHS, you have used joules. On your RHS, you have used watts. So for that, you have to balance the unit. For that purpose, what you will do is you will take the temperature variation with respect to time. And you can also take the temperature variation with respect to, sorry, with respect to temperature you have taken here. You can also take it with respect to the mass, but you are not going to take it with respect to the mass because mass is going to be the constant. It is not going to flow. Mass is not flowing in bulk. So here the temperature is only varying with respect to the time. That's why you have taken the temperature variation with respect to the time here, and then you have equated it with the Newton's law of cooling, HA delta T you have taken. So you have done some mathematical manipulation. You have taken this T minus T infinity onto this side and this MCP onto this side. This is how you will get, and then integrate. Then you will have initial conditions here. Okay. See, if it is a steady problem, you can solve it using the boundary conditions. Now it is not a steady problem. This is an unsteady problem. What you have to do, then you have to use initial condition. That is a temperature at with time, at so and so time. That is time is equal to 0 is nothing but the initial condition. So time 0, t naught you have taken, at time is equal to t you have taken, or simply t you have taken. So those things you have taken here, and with respect to those limits, this is a time 0 temperature, this is a time t temperature. With respect to those, you have taken, so, and you have integrated it. Basically what you have done is you have done a variable separable here. This is a temperature on one side, and time on the other side. So we have taken the appropriate temperatures and times in the integration. And when you do integration, 1 by x dx is log x. You have done the same, and integral dx is x. The same thing is taken again here. And the temperature limits on this side is substituted, and time limits are substituted on the right hand side. And then, so what you get is this one. And Krishna, please switch off your mic. Yeah. So this is the expression that you are going to get here. Ln of t minus t infinity by t naught minus t infinity is equal to minus h here rho VCP by t. You will get here. So then next thing is one more dimensionless number. It is Fourier number. You have seen this Fourier number is alpha t by LC square. Okay, this is actually non-dimensional time. This is like non-dimensionalizing the time here. Okay? If you look at the time here, alpha t by LC square, you have alpha is the thermal diffusivity meter square per second, and t is the time measured in seconds, and LC is the characteristic dimension. So what's happening is you may basically non-dimensionalize the time using the Fourier's number. Okay, you can see how the dimension is actually removed in this. So once you know that Baird number and Fourier number formulas, okay, so you can actually change this particular expression that you have here on your RHS. Under RHS, you can change it as minus but into Fourier. You can change it. So all the mathematical manipulation, I have done that, and I have written that this is equal to this way. That is minus but into Fourier. If I take out the logarithm and then write it, this is how it's going to look like. So if the bad number is less than 0.1, you can go for the lump. Okay, and then characteristic dimension. How you measure the characteristic dimension? The characteristic dimension is actually the ratio of volume by the respective area. Okay, so for cube, you will take the cube volume, cube area. It is a by 6, like that for all the cases. Whatever the given case that is there for you, you have to substitute and do it. So now let us solve a simple problem. So this problem is there in your document that you gave you, the Google Doc that I have shared with you. Hope you all remember that Google Doc. So in that Google Doc, we have this particular problem. All the problems that I'm going to solve in the class, that I have solved in the class, are available on that Google Doc. You can always cross-refer to that Google Doc. I have shared it with you already. You have that. Chance you are not having it, you please refer to your mail. You will definitely get that. Okay. So let's solve this problem. This is basically a lumped parameter problem, but in a given case, like in your exam and all, you will not know whether it is a lumped parameter or not. Okay, first of all, you have to find out that it is a transient problem. Okay, how to find out the transient problem itself is the first case, and the next thing is in the transient, all now among three cases, how do you find out is the next thing. Okay, so here I'm going to say that it is a transient because the word time constant is used here. Okay, okay, I must tell you what is a time constant before we go to this problem. Okay, see here, if you look at this particular expression here, like this is time and this is what? This is nothing but time constant. Okay, let me tell you. See here, this Biot into Fourier is non-dimensional thing. Non-dimensional into non-dimensional is non-dimensional. So ultimately, this is this value is actually you know 1 by the time unit is second. So this one will have 1 by second. So if I have to say what is time constant is represented with tau c. This tau c is equal to actually taken as a inverse of this, that is rho VCP by HAS. This is what is taken, and it is again measured in seconds. Okay. So that's what time constant is actually. So in this particular problem that we have taken, what is asking is asking you to find out the time constant tau c. Tau c means what? A rho VCP by HAS. What is this? He is asking you. Okay. So once you know that it is a transient problem, after transient, what you have to do is next thing in any given transient problem, what you have to do is you have to check it is lump or not. Okay. So how to check whether it is lump or not? You have to check for the Biot number. Okay, Biot number is HLC by K. You have to take. Okay. Before we do all that, let's write what is given in the problem first. Then it will be easy for us to do anything. So what is given a thermocouple. Okay, so it is formed by soldering end-to-end wires. The thermal diffusivity of the material is given. Alpha is given 5.3 into 10 to the power of minus 6. This is power minus 6 actually. There is a typo there. Alpha. And then thermal conductivity of the material is given. K is given as 19.1 watt per meter Kelvin. And T initial is given. That is T naught according to our nomenclature. It is 30 degrees centigrade. It's placed in a fluid. Okay, temperature of the atmosphere is given. Temp is in fluid. It is 600 degrees centigrade. Okay, and then this particular thermocouple is measuring the temperature of the fluid. If the convective heat transfer coefficient between the fluid and the wire, the convection heat transfer coefficient means H. It is 85 watt per meter square Kelvin. It is given. Then he's asking you to find out what is the time constant. He's asking you to find out for the probe and also the time taken for it to read 598 degrees centigrade. Okay, this part we will do later. First, let us concentrate on this time constant thing. Okay, so before we go into this, first we have to find out the Biot number. For finding that H is given, the H value is given and a K value is given, but you don't know what is LC. Okay, how to find out this LC? LC, I told, is a volume by area ratio. So what volume you will take here? What you know, whether you will take sphere or cylinder or what you will take? See, here he is saying that it is a wire basically. When it is a wire, it will be obviously a cylinder. So what I can do is the area is 2 pi RL I can take, and then volume I can take as pi r square into L. So if I take it, pi gets cancelled, r gets cancelled, L gets cancelled. So what I have is simply r by 2. So is also given the diameter in the question, that is D is equal to 0.5 mm. If I want to get this LC here, it is D by 2, that is D by 4. So you have LC with you now, you can calculate the biot also. So the biot will be equal to 85 into the LC is B 0.5 into 10 to the power of minus 3, because I want to convert this mm into the meters, and this should be divided by 4 by the K value is 19.1. Okay, so somebody calculate and tell me what is this biot number. Can you please calculate and tell me what is this value? Yeah, it's very well here. Wait. So the value we got here is 0.00056. Okay. So from this you can understand that Biot number value is well below your 0.1. Okay. So your lump is valid here. Lump parameter analysis is correct here. Okay. You can definitely follow it. So what you're trying to do is you're actually trying to find out this, time constant rho v cp by HEAS. We are trying to find out actually here. So for that, rho v cp by HEA value we are finding out. So now, just now, we have found out what is V by A value. Okay, that is, I can write this as rho Cp by H into V by A. So V by A value just now found out is D by 4. Okay, so this is equal to rho Cp by H into D by 4. D is given in question. You can simply do this, and this is H. The H that is there in the denominator is known to you. It is given in the problem. It is 85 watt per meter square Kelvin. So the denominator is known to you. Okay. So do you know rho and Cp? That is the question here. Do you know rho and Cp? That is a question. You don't know the values of rho and Cp. So how do you get the rho and Cp values? So for that, you must be using this alpha. Okay. For that, you must know what is the formula for alpha. Alpha is equal to K by rho Cp. Okay. So here in the problem, you know what is K and what is alpha also. Okay, because K is also given and alpha is also given. So what you can write from this is rho Cp is equal to K by alpha. You can write. So this will be like K by alpha into D by 4. So simply you can get what is tau C now. So K value is given as 19.1 in the question. The alpha value is given as 5.3 into 10 to the power of minus 6 in the question. And then D value is 0.5 mm, that is 0.5 into 10 to the power of minus 3 by 4. So then you will get what is tau C value. Somebody calculate this. Yeah. This value must be around 5.3 seconds. Okay, so that's yeah, first part of the question. Okay, in the second part, he has given you a temperature of 598. Okay, so what is this 598 and what is this 600? All these things you have to look into now. See, basically, what is your formula here? It is T minus T infinity by T naught minus T infinity is equal to e power minus of biot into Fourier. That biot into Fourier is nothing but minus HA by rho VCP into T. Okay, that is, you can write like e power minus of T by tau C. Okay, so that's the thing. So here in the question, he has given what is T infinity. The T infinity is given as 600. And T naught is also given. Initially, it is at 30 degrees centigrade. Now, it is at 598. That's what given in the question. Okay. The TC value just now we have found out it as 5.3. So only unknown is T, you have to find it out. So he's asking you to find out what is the time. So for that, what you get here is 598 minus 600 by 30 minus 600 is equal to e power minus of t by 5.3. So in this only unknown is t, you have to calculate it. Okay, you can apply the log on both sides. So what you get here is log of 598 minus 600 by 330 minus 600 is equal to minus t by 5.3 into log e to the base e is actually 1. So only unknown is t. You can find out the t value. This t value will be around 30 seconds. So that's how you'll find out the t here and tc here. I hope it is clear to you. If you have any questions, please ask me.